Okay, we've been looking at stretching springs. What happens if we stretch a material like a metal? So the setup is that we have a metal wire and we apply some weights to it. So this applies a force. What happens to the wire? Well, just like a spring, when we apply a force, it will extend. So we get some stretching, extension happening, which we'll call delta x. And if we plot this on a graph like we did for springs, we'll find that if we plot the force applied against the extension, that we get a straight line relationship. So basically the bigger the force, the bigger the extension, just like for springs. Obviously this doesn't carry on forever, there's something that happens eventually, but we'll look at that in a future lesson. Okay, I have a couple of questions now for you. So what I want you to do is to sketch the graph that I've drawn here, and then I want you on the same graph to sketch what the graph would look like if the wire was thicker, and what would the graph look like if the wire was longer. So basically you're going to have two lines added to this. What would it look like? Okay, when you have done your sketch, okay, then you can carry on with the video. Okay, so hopefully you've realised that if you have a longer wire, it will, just like if you have adding springs together in series, that if you have a longer wire, it's going to stretch more easily, okay, for a given force. So we'll have a line that's along like this, and for a thicker wire it's going to be harder to stretch. So for a given force there's going to be less stretch, so it's a steeper line like that. Okay, so we've seen that if we change the thickness of the wire and the length of the wire, both things will affect the way the wire extends. So if we want to compare different materials, what are our options? How can we make a fair comparison between the different materials? Okay, I'd like you to have a little think about this, so you can perhaps pause the video at this stage and then continue. Okay, you probably have thought about the first one. To make a fair comparison, you're probably thinking, oh, well, we should each time keep the length of the wire the same and the cross-sectional area. Okay, and then that is a possibility, but we can also do something called normalizing. Right, I want you to consider this. If instead of just taking the force, we take the force per unit area, then if we have different cross-sectional areas, we'll be able to normalize. So take that into account. If instead of just taking the extension, we took the extension per unit length, then we could take into account the fact that we have different lengths of wire. Okay, look at this first example. We have a cross-sectional area we'll call A, and we are going to put it in tension, so we're basically stretching it with a force F. Now, let's, instead of just recording the tension, the force, stretching force, we do force over area to normalise it. Okay, now let's consider the length. So here we have a length of wire, which I'm going to call, so the original length, L, and the extension I'm going to call delta L, change in length. Then if we normalise it, we have delta L over the original length. Okay, this thing, force over cross-sectional area, we call the stress, and this, the change in length over the original length, we call strain. And stress has a particular symbol, it's a Greek letter, and strain has another Greek letter. Okay, when we stretch things, like stretching our wire, we say we apply a tensile stress. Okay, it just means a stretching stress. You can also put materials under a compressive stress. Okay, so the forces in this case would be squeezing, compressive. Okay, but we're only interested at this moment in stretching things, so we're talking about tensile stress, tensile strain. Okay, let's have a look at the units for tensile stress and tensile strain. This is our symbol for stress, and we're saying that it's the force divided by the cross-sectional area. And you can see that this is just like pressure, newtons per meter squared, which is the pascals. The tensile strain is the change in length over the original length, and as you can see it's a length over a length, so it has no units, it's just a ratio. Now we can plot, instead of plotting force against extension, we're going to plot our normalized units, which is stress against strain. Okay, and we get our straight line relationship. Okay, and now, because we have normalized, we can compare all different materials and get a constant from the gradient which is comparable, and this constant is called Young's modulus. Which has the symbol E. So we get this from the gradient. Okay, so Young's modulus E is stress divided by the strain. It's the gradient of our graph. Okay, and these are the symbols. And so what about the units for Young's modulus? Okay, so we have the units for stress, which is pascals, divided by, and the units for strain was a length over a length, dimensionless. So, in fact, it gives us the units for Young's modulus is just pascals. Typical values for Young's modulus are, for steel we have 2.1 times 10 to the 11 pascals, copper 1.3 times 10 to the 11 pascals. So basically very large numbers.